So good evening. We're thrilled to have with us tonight Fred, K3CSX, one of our most active club members. Fred is our club secretary, membership coordinator, and most notably, a longtime stalwart member of our repeater committee. Tonight, Fred will talk to us about repeater duplexers. So thank you, Fred, for all you do for our club and for amateur radio. And now it is over to you.
All right. Well, thank you very much. I appreciate the opportunity to give this presentation. Let's see if I can this time successfully start sharing. Hopefully you see my entire screen, the presentation.
Yes.
All right. Excellent. Okay. The meeting's being recorded. All right. So the presentation that I wanted to give today is about repeater duplexers and how come repeaters have them, because we don't usually have them on our regular radios. So again, all right, there we go. So some of the things that I want to talk about today, and hopefully we'll get an idea about, is to understand what's unique about repeaters and the way that they receive and transmit, that's different from our regular transceivers. Understand the ways to mitigate issues that arise when you have the transmitter and receiver sharing some resources, and understand the purpose and use of duplexers. And I will say that this is, I guess, sort of an introductory or high-level view of kind of like what we have or why we have them and generally what they do. And if you really want to understand how duplexer actually works and is designed, that's something I'm going to leave to you. All right. So we're all used to our regular transceivers, like the mobile rigs that we have or the base stations that we have at home. And it really doesn't matter if it's 2 meters, 440, HF, 6 meters. They pretty much all work the same way. And so the one thing that's different about them is, of course, inside your radio, and you never really notice it, although you may hear a click when you switch between transmit and receive, is there's a transmit and receive switch. And what this switch does is it says that if you're just listening, whatever is coming in from the antenna on the receive side is routed into the receiver component of your transceiver. And then, of course, the audio comes out of the speaker. Now, as soon as you key up the microphone or key up with a key if you're doing CW, then the switch says, okay, well, now it's time for the transmitter. So whatever you're keying or speaking here goes into the transmitter portion of the transceiver. And because of the TR switch, that's what's going out of the antenna, but you can't hear anything because this side is basically shut down due to the TR switch. Oh, is my pointer showing up when I'm doing
Yep.
stuff like it? Okay. So let's see here. Whoops, went the wrong way. Okay. So the thing about repeaters that makes them different is that they simultaneously receive and transmit. So and usually they're doing it within the same frequency band, like VHF, UHF, 6 meters. And so you have basically trying to hear a very weak signal coming down the antenna and in the in the coax into the receiver portion of the repeater. And at the same time, that same thing that you're saying is being transmitted out the transmit side and going up the feed line to the antenna. So you have a little bit problem here is that the receiver is extremely sensitive, something in the order of being able to pick up a signal that's a quarter of a microvolt. And then, of course, you have a transmitter that's extremely powerful, like 100 watts. And part of what makes that kind of difficult is that you have to realize that both of them are connected to the same feed line and the same antenna. So although the receiver is trying to listen for a very weak signal that's a quarter of a microvolt, at the same time, your 100 watts is going out there. And believe that the calculation is if you convert 100 watts into volts, it's 71 volts, which is the equivalent of 71 million microvolts. So you have this very uneven process going on here. So the way I look at it is in a simplistic view is so this is the perception of the how this stuff it works based on the repeater receiver. So the receiver is extremely sensitive, just like this guy is like very intently listening to just the little microscopic sound of tumblers clicking into place on a safe that he's trying to open. But then the problem is the transmitter keys up, whoops, and now you have this. So the transmitter is much more powerful, and it's kind of like having a guy trying to open the safe with a drill at the same time. Obviously, the guy who's listening very intently isn't going to hear anything other than the drill. So this is sort of like the reason why we have to do something about this in a repeater. So what we need to do is try to figure out some way to keep the output from the transmitter that's very powerful, like I don't know what 71 million times a quarter is, but it's a big number, right? So there's this massive amount of voltage going out. At the same time, the receiver is trying to listen to a microvolt. And what will happen is it basically gets deafened. And this is what is referred to as desense or desensitization. And you may hear that term from time to time. People talk about like repeater desense, so that for whatever reason, the sensitivity of the repeater goes down when it's transmitting. So I might hear somebody very well when they first their signal first comes into a quiet repeater, and the minute the repeater keys up to retransmit their signal, it can't be heard anymore. And so what you need to do is somehow isolate the transmitter and the receiver from each other so that they don't interfere. And the way this isolation is done is it's usually measured in decibels, so many decibels of isolation. So there's a couple of different ways to provide isolation between the receiver and the transmitter. The one way is to use frequencies in completely different bands, which is what's sometimes used referred to as a crossband repeater. A common example of that would be a dual band mobile rig that has crossband capability. So typically what will happen is I would set my radio to transmit on the repeater's frequency 146.355. But then maybe I have a handheld that I'm away from my car, and it's transmitting to my vehicle on like some UHF frequency. And then that radio that I'm also carrying in the field is also dual band. So when I unkey on the transmitter, it's listening on 146.955, so it'll hear whatever's coming back out of the repeater from somebody else. Like a response. So that's a really common way to do it. And sometimes there are some repeaters that do that. I think like the Jessup repeater and even some 10-meter repeaters might have this capability where I know for the Jessup repeater, they have receivers on UHF, but they all transmit on 146.76 in addition to listening on that on 146.16. So another way you can do it is to physically separate the resources being used by the transmitter and receiver. So typically that's done by uh, separating and using separate antennas and separate feed lines. So therefore, you don't have this problem of what the transmitter is sending out is going out the same coax and out the same antenna as the receiver is listening on. Um, but if you're still in close proximity, that's still going to be a problem. And I bet people have noticed that if you have two people, well, we've actually even noticed that sometimes at field day, right? That as soon as one station keys up in the same band that you're in, it interferes, or you may hear them. Um, and then the other way you can do it is to use a duplexer, which does allow the receiver and transmitter to share the same antenna and feed line. And the duplexer takes care of isolating the signals between the two sides. So, talking about some of the different ways to do the isolation. Um, so the physical separation would be, an example of this, that you have your repeater here in the center. And what happens is it has audio coming in from a separate antenna through the receiver, and that receive audio goes out to the controller, and then it transmits out, goes out to the transmission section, and out a separate antenna. So now you don't have the problem anymore of both the receiver and the transmitter listening on the same resources or using the same resources. And the separation can be done sort of two ways. You can do it vertically by having one of the antennas higher up on the mast than the other one, or you could also do it horizontally by spreading them apart. And it turns out that it's more effective if you have them separated vertically than horizontally, because like 10 feet of vertical separation provides about the same amount of isolation as 30 feet of horizontal. So that's a common way to do that, is to have them on the same mast, but have one up at least 10 or more feet higher than the other one. And I think I don't know if somebody has worked with us on field day, but I know like at the net control station we have this problem where we have three different race nets going on. They may all be using same, in the same band frequencies, like two VHF repeaters. And the way we kind of do that is by putting them on the same mast, but separating them vertically. And we've tried it also horizontally too, but we found the vertical separation works much better. Um, and the lower the frequency you have, the greater amount of separation you need. So it doesn't require as much separation on like the 440 band as it would on the 2 meter band. So the other way to do this is with a duplexer. And again, it's similar to the original idea that we have with our own personal transceivers, except that you have, the same antenna. So if we think of the repeater as being basically here, where it says controller, so a signal comes in, the duplexer routes the received signal to the receiver side, and then the receiver audio is fed to the controller, and the controller takes that audio and sends it out to the transmitter, and it goes out through the transmit side of the duplexer, up the same feed line and out the same antenna. Um, and this, this is kind of pretty much how almost, I'd say, most of the amateur radio repeaters work. There are some that do use separation or have separate sites for the receiving. Ours, actually, if you think about it, on our repeater, because we have 4 remote sites, if we take and turn off the receiver at the main site, then basically all the green stuff here doesn't exist anymore. And if all the signals are coming in through a voter from other remote receivers, then we don't have this problem. This is the repeater just is doing the transmitting on the feed line and antenna, and all the reception stuff is coming in out of band on link frequencies, which are in our case UHF. So that sort of provides the separation that we need. But as soon as the main site has or its receiver enabled, then you do have this issue about the possibility of descents. So, what is a duplexer? So this is sort of a picture of a duplexer, and to me, it's sort of magic. And somehow, it's a device that allows the bidirectional, hence the term duplex, communication within the same band, but separates the receive and the transmitter from each other while they share a common feed line and antenna. And like I said, if you looked at one, it looks like a bunch of canisters and interconnected by coax. And how they work to me is magic. Again, if you really want to know the theory behind how you design a duplexer, you'd have to go somewhere else. I don't really understand that. Um, so it does provide the service that we're looking for. And so let's talk about how we use it, not how it actually internally works. So again, what you expect your duplexer to do is make sure that whatever signal is going out your transmitter doesn't get into your receiver. Make sure that other transmitters that might be nearby don't get into your receiver, and make sure that your transmitter tries to stay out of any other nearby receivers. And then what this does is also helps prevent mixing of transmitter output with input or other output. And this is what people refer to as intermod. So if you have our transmitter on 146.955, and there might be another repeater nearby that's transmitting at the exact same time, you have this possibility that the effects of adding, subtracting, and some differences may end up causing intermod or transmission on another frequency, which we're trying to avoid. And that was like, I think sometimes some of the things we noticed in the past, because where our main site is, there's a lot of other transmitters there. And I think, one time, I guess Montgomery County had a lot of stuff there. I think they still have some stuff there. But if you remember, there was a time where all of a sudden we would hear Montgomery County ride-on transmit coming out of our repeater. And that was because whatever was happening at the time, their signal, which was happened to be on UHF, was mixing with some other signal. And it was some, um, uh, what's the word I'm trying to think here all of a sudden? Multiple of our frequency. And then some of that ends up, we hear it as 146.355. So our repeater transmits it. Fortunately, that we were able to get rid of when they moved away. Okay, so that's what we want our duplexer to do. And so some of the things that give you that characteristic of a duplexer is that they operate in the frequency band that the receiver and transmitter is. So, we have them on the 2-meter repeater, we have them on the 440 repeater, and we have them on the 6-meter repeater. And what they have to be able to do is handle the output power of the transmitter, because all the output from the transmitter is going to go through the duplexer. They need to get rid of any transmitter signal on the receive frequency to make sure that your receiver doesn't hear it. And they have to do this within a relatively small frequency range. Now, in the case of 2 meters, that's only 6 kilohertz apart. When you get to 440, we're 5 megahertz apart, so that's not quite as bad. And some of the other bands, I think 220 is something like 1.5 megahertz apart, and I think 6 meters is 1 megahertz apart. Is that right, Mark? Shake your head if I'm right. Okay, thank you. So again, but when you get to the lower frequencies like 6 meters, the problem isn't quite as bad as it is on the higher frequencies. So again, the duplexers are basically metal cylinders, and the size of them is determined by the frequency. So for example, this is our 2 meter repeater, and these three things sitting on top. There's actually a total of six there. There's three more stacked on top of it that's not showing in the picture. But these cylinders, I don't know, they're maybe a foot in diameter and maybe 4 or 5 feet in height. But if you were to look at the ones for the 440 repeaters, those are the ones that are so small we can fit them right in the cabinet. And a duplexer for 440 repeater is, a lot smaller cans because the frequency is higher. I don't have a picture of it, but I'm sure if you went to see the 6 meter duplexers, I've seen them before. They're probably somewhere in the size of maybe 5 to 6 feet high and a much bigger diameter. So again, these are designed when you buy them for the particular frequency that you want to use them on. They have to be rated at the power that you need and have a high Q. So what the Q is, it's a ratio of the frequency that is resonant or sort of will pass through to the whole bandwidth. So if you have a high Q, that means that you have a very narrow bandwidth, which is what we're looking for in the case of a repeater, right? We want only a frequency that is the transmit frequency or the receive frequency to get through the duplexer and not much on either side of it. If you had on the conversely side, like for example, maybe your repeater or excuse me, your antenna that you use for your HF, for example, may have a lower Q so that has a bigger range within, say, the 10-meter band. So in talking about the Q that we're just referring to. So this is sort of like a picture, if you will. So as I mentioned, so Q is equal to the resonant frequency over the bandwidth. So again, the idea is that by having a smaller bandwidth, then the value for Q is going to go up given the same frequency. So this is kind of what we're referring to is like, for example, this turquoise line. Um, if the resonant frequency is right here, let's just pretend that's 146,955. If there's an antenna, or excuse me, the duplexer has high Q associated with it, then it's got a narrow bandwidth. So only a relatively small amount of signals will go through. Anything that's over on either side of it is very drastically cut off. Whereas in the case of a low Q, which we don't want in the case of repeater duplexers, you have a broader range of frequencies that would make it through. And the other thing that you have to do with these filters is since you are feeding your transmitted power or your received microvolts through them, you want them to have low loss, right? You don't want them to be a big attenuator and basically make your receiver deaf or have a high amount of loss on the transmit side, which really cuts back your power and your repeater won't be heard as well. So, excuse me. For the cavity filters, there's basically two kinds. One is referred to as a band pass filter, and that's because it passes a very small band of frequencies and rejects anything else. And then we have band reject or notch filters that reject a specific range of frequencies and all the other frequencies pass through. So if you kind of look at it with this little diagram down here, um, a bandpass filter only transmits at a certain frequency. So let's say this is our 146,955 frequency. We want the bandpass filter to only allow that as much as possible. Anything that's on either side of it very rapidly drops off because of attenuation, and therefore it doesn't get sent out the antenna. On a notch filter, it's just basically the opposite. You have like all this RF coming into your antenna, and you have the frequency that you want to listen to, which is like 146,355. And what you want to do is you want to have um, basically no isolation um, of that. And then anything that's outside of this range, as you get either higher or lower, has a lot more isolation. Actually, the scale should be reversed on this one, but I think I must have cut it off. So that's the idea of like a band pass, um, allowing only certain frequencies through a very narrow amount, and a notch filter keeps certain frequencies out. I'm sorry, actually, I said I made this wrong. Let me go back and re-clarify this. So the bandpass filter is allowing just a small frequency through. In this particular case, the notch filter, let's say our transmitters on 146.955, what we want to do is make sure that anything that gets on the receive side that's at that frequency is basically attenuated, as much as possible. And if it's, stuffing that's on not on the transmit frequency, basically the receive frequency, which is nearby, then that has almost no attenuation. So that's the main difference between the notch and the bandpass filter. So this kind of like shows how these things are put together. And again, I do not understand how, this is sort of like a diagram of what a bandpass cavity filter looks like. And I know that you basically, it is tunable, and there's this tuning knob on top that raises and lowers a rod inside of this um, cylinder, and that basically fine tunes the frequency for what frequency is going to get through it. So you have the input coax coming here, and then through these coupling loops, things that are at the right frequency within the band pass that it's set for will allow it to go out the output side of the cavity, and that might be going into the receiver's input. So the thing that's kind of important to this is you have these two connectors and two loops inside. And so these are set in series, just like a battery. You have a connection in and a connection out. The way you combine, so this is basically a band reject or a notch cavity, and those are connected in parallel. And what's different about them is you basically have a T connector. And so your, let's say the coax from the antenna is coming in here on the right side of this T. And then coming out the left side of the T is the feed line going into your your repeater's receiver. So the signal comes in here, and if it's not rejected by the cavity, then it makes its way through. Anything that's outside in the notch range just doesn't make through this. How it does it again, it's magic. I don't know. Seems to me if the frequencies get buried in here somewhere, that thing is going to fill up someday, but I don't know how it works. Um, but anyway, it's sort of again magic, but this is one of the characteristics of the notch filters is how they're connected. And typically, a repeater, when you're setting it up, you would use a combination of both notch and bandpass filters. So, for example, here's our antenna, and it's coming down. And of course, both the receiver and the transmitter are sharing the same antenna and feed line. So now basically that line splits with a T connector, and half of it goes into the receiver side of the duplexer. And so the first thing usually we have is a bandpass filter. So the bandpass filter only allows things like, say, within the 2 meter band and close to the R frequency that we're on. Then the output from that goes into a notch filter. Now, the notch filter will be set to reject our repeater's transmit frequency. So basically, we want to make sure that whatever our repeater is transmitting isn't going to make it into our receiver. And then there sometimes you have to have a second one because each one gives you additional amount of attenuation. And again, because the transmitter, which has got stuff going out the same coax here, is very powerful. You want to notch out as much of that frequency as possible. So on the receive side, that's typical to have a bandpass filter to just get the 2 meter band that you want, that's a small segment of it, and then notch out the signals that you don't want, which primarily is the frequency that you transmit on. On the other hand, on the other side, we have the transmitter, and it's transmitting, and what we want to do is notch out specific things that we don't want to go out, which is basically any of the signals that are on our receive frequency. So we don't want them mixing and possibly causing intermod. Plus, again, we kind of do that with two notch filters, and then finally a bandpass filter, which basically says, well, the only thing that's going to go through this and come out the other side is stuff within that narrow range of our transmit frequency, which is 146,955. And so this is basically a kind of a common way. And our repeater has something very similar to this. There were six cavities, a combination of notch or reject and bandpass filters. So this is kind of like trying to show the example of how it works with a duplexer. And so the frequency here isn't our frequency. I got this from some other diagram. And so, but it's similar because it's 2 meters. You can see it's receive is, or excuse me, I'm sorry. In this case, the transmit is 145. I'm sorry, no, that would be the receive. Yeah, receive. The receive frequency is 145, 175, and the transmit frequency is 145, 775, or 6 kilohertz higher. So now if we look at the receive path, which is just this blue line, what we want to make sure of is that our signal that's going through the receiver, if it's at the receive frequency, we want no attenuation. So that signal has a strong signal strength. And if it's over here at the transmit frequency, we want to attenuate it as much as possible so the receiver does not hear anything on the transmit frequency. So that's why we have, minimum attenuation on the input frequency and maximum attenuation on the output frequency. Similarly, if you look at the transmit side of this, on the transmit side, which is the red line, we on the transmit frequency 145,775, we don't want to attenuate that as much as possible. We want to let all of our all of our transmission on that frequency to go through, but we don't want it to hear anything on the input frequency. So anything that's basically on the input frequency has the greatest amount of attenuation. And of course, you still have some attenuation, outside that range as well. But the idea is, again, minimum attenuation on your transmit frequency and maximum attenuation on the transmit frequency. So that's basically how duplexers work. Like I said, we have them on all our repeaters have them because all our repeaters at least have transmitters and receivers on the same site and on the same feed line and coax. So hopefully we're not going to ask too many hard questions, but I'll certainly try to answer them if you have them. Either nobody can unmute or I did a super job of explaining this. All right.
If people, okay, so I'm unmuted. Terrific presentation, Fred. Thank you. Paul isn't here, so I muted everybody. And so I don't know, if somebody has a question, if go ahead and unshare, and then we'll just,
Okay.
yeah, and because I'm struggling. I really miss Paul doing this because he makes it seem so easy. But so if anybody has a question, if you can raise your hand or um
Did I stop sharing? Okay.
it's not working for me. I'm not sure.
Okay, hold on, hold on. Let me click that again.
There we go.
Okay.
All righty. So if people have a question, see if you can unmute yourselves.
You can.
Okay, great. So if anybody has a question, I know that that was a very comprehensive and very interesting presentation. So thank you. And any questions? I think you wowed them, Fred.
Yeah, actually, I think I gave that presentation previously just to the repeater committee because, when we were sort of getting a new repeater committee formed, that is probably the most complicated part of our it's most complicated part of almost any repeater. Maybe on our 2 meter repeater, the voter is the thing that's even more complicated. And maybe someday I'll tackle that and sort of explain how that works. But for most repeaters, the duplexer is the important part. And if you have your duplexer mistuned, you're just not going to have a well operating repeater.
Yeah, yeah. So Rich has a question.
Godrich.
Yeah, Fred. Great presentation. You may have covered this, but I think I may have missed it. But when you purchase a duplexer, do you ask or do you tell them what frequency you want it tuned to?
Yes. And like if you actually looked at our I don't know if it's true if it's on our 2 meter duplexer because they're so big, I haven't really looked at it. But I know if you look at the 440 duplexer, because they were all together in a little rack, the four canisters were sitting just next to each other, and they came on a rack, and if you look on that rack, the company that made them tells you what the receive and transmit frequencies are that they were set to. Now you can adjust that a little bit through the tuning. If you find that over time, because of heat and cold was going to cause things to expand and contract and maybe cause some detuning, you can fine tune it. But like for example, if you had a repeater that was on the low part of 2 meters, like that example 145, 1575, and then you tried to use it maybe at the upper part, like one of the like 147, 300 and 146, 900, I think, input. That's probably too far apart that you probably won't be able to make the adjustment just with the tuning knobs. You may just actually have to need to get a new duplexer.
Okay. And another quick question. Are the duplexers susceptible to temperature change? Will they drift or will the either the notch depth or the bandwidth peak, will it shift if they get hot or cold?
Yeah, I mean, theoretically, that is correct because again, they're metal and metal expands in the heat and contracts with the cold. But the effect of it, I don't know if it's just the way they're manufactured that they're less susceptible to that expansion and contraction to other things. I mean, I think the walls of a duplex are pretty thick. And I have not noticed that we had to go like in the summer and winter go up twice a year and retune the duplexers. It's been pretty rare that we've had to retune them.
Okay. And are they just filled with air, or they have a vacuum, or are they hermetically sealed?
No, I believe they're just filled with air. I mean, you can
Okay.
take the top off clean the inside out and put the top back on. You don't have to like do it in a vacuum chamber or, pump nitrogen in it or anything like that. They're definitely not fluid filled. It's just basically air. And so it's just
Okay.
the difference, I guess the distance between the center conductor and the sides that have something to do with how they get tuned, and then where the end of the center conductor is vertically within the cavity has something to do with, again, the fine tuning of it. But they're not specifically on a specific point. If you remember from those diagrams, on the notch filter, the kind of like goes up. It's pretty narrow, but it's not like, just a closed thing. So I think that's what helps you in the temperature extremes. Like you might be a little off on one side during the summer and a little bit off on the other side during the winter, but it's still close enough to have the effect that you want. And I guess if
Yeah.
it's really important, then you put them in cabinets that are air conditioned. I know that I've seen at our main site, there's equipment that's up there that has little portable air conditioners attached to them,
Right.
and that's
Yeah.
commercial
Okay.
stuff.
Okay. Thank you very much for the
Yeah, good question.
So Mark has a question.
Well, not so much a question as an expansion on what Fred said. If you notice the pictures or diagrams of the containers, they are filled with air, which tends to, shall we say, slow the process of the heating up or cooling down of the tuned sections. And as Fred so appropriately pointed out, yes, there may be some change, but it's going to be relatively small. And for the most part, will be not noticeable. If you put a piece of lab equipment on there to see where the notch frequency or where the bandpass peak frequency was, sure, you could see a temperature change, but it wouldn't be significant enough to make any difference. So that's all I wanted to add to that.
Yeah, that's a good point. I forgot. Air is a great insulator. That's why we use down and multi-layers of clothing.
I guess humidity wouldn't play a part in that either if the air was humid inside.
Um, I mean, when people usually work on them, they work on them. I mean, like ours, like when Al and W2M used to, work on them, he might take them home and then do it like in an air conditioned place. So basically, the air that's in it is, relatively dry and stuff like that. So, and then once it's shut and it's tightly shut, there's a gasket and everything. And a lot of times the tops are riveted on. You're not going to get a lot of moisture in or out of there. But actually, I mean, it is true though that corrosion can occur. There is moisture and sometimes there do get some corrosion. And I think in the past, not the current set of duplexers, but the ones that we had before that, I mean, I think they had to be taken apart one time. We're getting a lot of crackly noises, and that's usually an indication that there's some sort of buildup in there that's basically causing little micro arcs from occurring and disturbing the function of the duplexer. And so I know like Al had taken them apart, cleaned them out, and put them back in service again.
Okay, any more questions? All right. Well, thanks, Fred.
You're welcome.
Great
I really
information.
appreciate the opportunity to do this.
Well, we appreciate the opportunity that you gave us to. Oh, Eugene's got a question.
I was just going to comment that um, duplexers that lose their seals will fail just because of the corrosion. We had an issue, I think it was on our 2-meter repeater, maybe 10 years ago, where I think we had that occur, and it ended up killing the power amp. So we were running barefoot without the amplifier for a while because of a reflected signal that basically did not do nice things to our transmission amp. Fred can probably recall the dates and the specifics of that better, but we did put in a device which will now take reflected signal and actually reroute it into a dummy load to protect the amplifier. So back to net. Oh, and let Fred comment on that.
Yeah, so you're right, and that's what I was referring to about the corrosion inside and how it, I mean, and it may be that that was the reason we have the new duplexers that we have now, that it may have been the corrosion was so bad it really couldn't be fixed. Um, the other thing is that what you're saying is true. They put in a device, I think it's called a recirculator, and so whatever comes back down the feed line goes into this, and then it routes it to a dummy load to make sure that the output of the transmitter doesn't, get shorted. And the problem with the duplexer can be a common issue that might cause that. Another one we had, and fortunately the thing was there, was when we had a case where a contractor was supposed to remove some antennas, and they were given either the wrong information or they misread the map of where the antennas were located on the roof, and they actually took down our antenna and cut our coax. So, I mean, that would like be just like absolute, disaster. The transmitter's trying to transmit 75 or 100 watts into nothing. But fortunately, the recirculator saved them.
Okay. Thanks, Fred. And we're going to upload this on the YouTube. I know some people missed part of the presentation in the beginning, but we're going to upload this to YouTube so you can watch this all over again. It's great information, and I'm sure a lot of people, in addition to our own club members, are going to find this very useful. So thanks a lot, Fred. Okay, so that's it for tonight. Thank you to everybody that came, and especially to Fred for all the information he's shared. And if there's no objections, does somebody want to make a motion to adjourn the meeting?
Mark raised his hand.